So here is one. Here is a hexane in hexane here, right? Here is in hexane, and here is a isopentane one two. Yeah, isopentane here, right? So here is isopentane, and here is a n-hexane, right? So both are the isomers one. Okay, chain isomers. These two are the chain isomers, and these two can be differentiated with the C30 spectra. NX is the three, right? So you can see here because it is 1, 2, 3. It is so we get only 1, 2, 3, three non-equivalent three set of carbons here. So we get the three signals, and this isopentane, right? Isopentane is giving four signals here, right? So because these two are same, right? So these two are same here. Yes, so these two are same here. One signal for this, and here 2, 3, and 4. Right. So there are four signals are possible for this particular isopentane. Right. So by this and with their delta values also. Okay. So in the in hexane we have the, right. So because the C1 and C2 both are same here, so we have the delta value at 14.1 because alkanes having the alkanes falls in the upfield or the shielded region. Okay, so and C2 and C5 is shown appears at 23.1 delta value. C3 and C6 32.2. Right. So here also in the the C13 spectra of your isopentane, where the C1 and C5 appears at 22.2 here, and C2 at 31.1 and C4. So by differentiating these delta values, okay, we can identify the structure of that compounds, or we can differentiate the compounds here. And you can see the spectra of various isomers here. For example, 1-chloro, 2-methyl propane. Here is a 2-chlorobutane. Okay. So 1-chloro, 2-methyl propane, it is having three signals, and the 2-chlorobutane, it is having the five signals here. Sorry, four signals here. Right. So with 2-chlorobutane. Okay. So with this 1, 2, 3, 4. Right. So four non-equivalent carbons are the four set of carbons in the 2-chlorobutane here. So we get the four signals at 5, sorry, at 10, and here is a 24 and 36 here, and here is 60. Right. So four signals with the delta values, and it is a 2-butane. Okay, 2-butane here. This is 2-butane. So we have this this A and A. So B, right? We have two signals, right? But 2-butane, there is a two signals. Okay, so it is symmetrical. So we have two signals here. At here is a, because it is alkane sp3 carbon, right? So sp3 carbon, so it appears in the range of where it is like it is 6, 5 or 6 something. Okay, 5, and with, because it is sp character here. Okay, triple bond, so it appears in the range of 66 here. Okay. So like we have various examples under this structure identification. And one more application is we can identify the correct structure. Okay, we can identify the correct structure for the compound here. For example, here the okay, so here the cyclotetraene. So under thermal conditions, generally it gives exist in the dimer form, right? So under thermal condition, so in the photochemical reactions, so this cyclo tetraene, cyclooctatetraene, okay, cyclooctatetraene. So it exists, it forms the dimer here. Dimerization takes place. Okay. Uh, so this for this dimer, there are three, right? There are three possible structures are proposed. There are three proposed structures are there. And which structure is correct for this one? So we can identify with you can decide the final structure or the correct structure for this dimer formation with the C13 spectra. Okay. So here the three possible structures are given, like this is one, structure two, structure three. These three are the possible structure for the having the dimeric form of the cyclooctatetraene. Right. So with here, okay. So this is the correct structure for this one, right? So and that will be identified with the C13 spectra. So generally the dimer, which is formed by the photochemical reactions of cyclooctatetraene, it gives a four signals, right? So this structure is giving four signals, and remaining structures 2 and 3 is not giving four signals here, right? So this giving how much it is? It is 1, 2, 3. Sorry, these two are same one. These two are same two. These are three, and here is 4. Here is 5, right? And here is these two are same 6, 7. So it is giving 7 signals here, right? It is giving 7 signals. It is giving 4 signals, right? And it is giving some this also some 7 or 8 signals here. So in general, okay, so this the dimer supposed to give us 4 signals here. So we can identify, or we can finalize the structure is this one. This is the correct structure here, right? So that is also advantage of this one. And one more application with this C13 spectra is, right? So here is a warfarin, right? So here is a warfarin, right? So warfarin, it is a anticoagulant here, right? So anticoagulant, so it's used in the blood clotting. Used in the blood clotting, like what is that? So vitamin K, you know that, right? So you are aware of, right? So vitamin K here. Vitamin K is uh, used for the blood clotting here, anticoagulants. Okay. So this warfarin also used for the blood clotting or the anticoagulant here. Okay, and its structure, right? So where we have a doubt that which structure is correct for this uh, anticoagulant warfarin, right? So there are two structures are proposed here. Okay, one is a right, so cyclic structure for this, and another is a acyclic side chain structure here, right? So here we can see, right? So where this it is having the ketone, right? The open chain ketone structure here, and one more structure is in the form of hemiacetal structure, right? So here it is hemiacetal. Okay. So we have hemiacetal structure, and the open chain structure where this right. So this open chain structure, this open chain ketone structure, right? So which structure is correct for this particular warfarin, right? So we have an idea about, we have a doubt about this one. So which is the actual structure of this warfarin? So then it is revealed, right? It is revealed by the C13 spectra is where the, okay, the hemiacetal structure is the correct structure for this warfarin, okay? And generally it is identified by with the C13 spectra. When the C13 spectra is recorded for this okay, warfarin, so they got this right. So one signal at 216, okay, right. So they got the 216 here, okay, 216 and the other 160 for this that is what is that cyclic keto sorry, cyclic ester, and 216 for this open chain ketone here, right? And when the warfarin hemiacetal structure is observed, right? So they got the signal at 200 ppm. The new signal is appeared with the 216, okay, ppm delta 216 ppm signal is absent here, right? So it is disappear. Okay, it is disappear. So then they got the conclusion that, okay, so where this particular ketone is, okay, this open chain ketone is okay, so this open chain ketone is locked in the hemiacetal formation, right? So here this sodium salt of this okay, sodium salt of this warfarin. So when they are taking the sodium salt of warfarin here and they observe that, so it may be further converted into here is pH is methane, okay. Right. So it is this ketone, okay, so this ketone structure is, it is locked in the hemiacetal formation, right? So the correct structure for this warfarin is when it is in the open chain structure. This is the open chain structure for this warfarin here, and this is the cyclic structure. So both the structures are possible for this one. Okay, so by hemiacetal formation, okay, so the warfarin is existing in this open chain structure like your glucose, right? So glucose is exists in the two forms, cyclic form. Okay, so here is a this is an open chain structure of glucose here, and cyclic form of your glucose is this one. Okay. Okay. So this is cyclic form. It is open chain structure. So like this glucose, for warfarin also we have the cyclic open chain structure, cyclic hemiacetal structure, right? So that will be known by C13 spectra here. And the conformation analysis. So here also, this is also one of the important application, the conformation analysis. So you can identify the correct conformation of the cyclic alicyclic compounds like cycloalkanes or the cyclohexane here, right? So you can propose the correct conformation for this cyclohexane with C13 spectra. Okay. Here in this example, you can see this particular cycle. Okay, the chair form of your methyl cyclohexane. Okay, chair form of your methyl cyclohexane. At room temperature, it gives only one signal here. Okay, at room temperature, like 27 degrees Celsius temperature. So it gives only one signal. And at very low temperature, it gives two signals here. Okay, so you can observe this. So at room temperature, it gives only one signal. Okay, and at low temperature, like minus degrees, minus 10 or minus 20. Okay, so at minus 10 degrees, so you get the two signals here. So why we are getting these two signals at low temperature, and why we are getting the or one signal at high temperature or the room temperature here? So generally at room temperature, okay, so at room temperature with the rapid conversion, okay, the rapid interconversion of this axial methyl to the equatorial methyl. Okay, so at equilibrium, with the axial methyl is converting into equatorial methyl here. Okay, this is axial, this is equatorial. So this conversion takes place, but where it is a rapid conversion, the rapid interconversion, a speedy interconversion takes place at room temperature. That's why the instrument won't recognize that methyls here, in what position it is attached, whether it is oriented axially or whether it is oriented in the equatorially, right? So these, the instrument cannot be differentiated because the rapid interconversion, very speedy, okay, speedy interconversion takes place here. So uh, irrespective of that, the position of that methyl here, so the instrument gives only one signal for this axial and equatorial. But at low temperature, okay, so very slow interconversion takes place. So the instrument recognize, okay, it gives one signal for the axial, another signal for the equatorial. So two signals are obtained with their different delta values. Like equatorial obtained at means absorbed at 20.8 delta value, and axial methyl group, it absorbs at 11 to 12, okay, delta ppm, right? So because at very low temperature, the slow interconversion takes place here. That's why the instrument can be easily recognize the presence of the axial and equatorial methyls here. And here also same, the one more example, like at 40 degrees Celsius, 1,2 dimethyl cyclohexane shows four signals here. Okay, so here the temperature, the condition, you can see the condition first. Okay, at 40 degrees means higher temperature. More it is more than room temperature, because the room temperature only is 27 degrees. Okay, but here uh, at 40 degrees, 1,2 dimethyl cyclohexane shows four signal here due to rapid interconversion. Okay, and at minus 100 degrees Celsius, it gives a 8 signals here. Okay, so here is a molecule where the 1, 2, 1, 2, 3, 4, 5, 6. Okay, so 1, 2 dimethyl cyclohexane at 40 degrees. Okay, at 40 degrees, it gives a four signals here, and at minus 100 degrees, it gives 8 signals. Okay, so here you can explain these the differentiation of these. Okay, the means the formation of the appearance of the different signals here with okay, so you can explain with this particular the criteria of the temperature here. Okay, at 40 degrees, generally it is very high temperature here. So rapid interconversion takes place. So we get four signals for this. Okay, and at minus 100 degrees, so very slow, means very cold condition. Minus 100 means it is very cold condition. So at cold condition, generally the rate of reaction is very zero. Generally, it is negligible. Right, very slow reaction, and generally the reaction won't take place. Generally, minus 100 means very it is a cold condition here, highly cold condition. So the reaction won't take place generally. So the compound is in the ground state only. So where all the carbons, okay, all the non-equivalent carbons uh, appears at their different delta values here, right? Because in the cyclohexane, right? So in the cyclohexane, actually we have the six types of carbons, right? Six types of carbons here. Six carbons having the six types here, because it is substituted. If it is unsubstituted, then we have only one signal here, right? For cyclohexane. Okay. So it is unsubstituted. So all are equivalent. So one signal. But if it is substituted here, right? So it is substituted, then we get eight signals for this 8 to 100 degrees temperature. Okay? The different, the means getting the 100 means 8 signals, 8 to 100 minus 100 is due to that particular, okay, so the non-taking of the reaction here. And the differentiation of geometric isomers. So cis-trans isomers also can be identified with this C13 spectra. And study of reaction mechanism. This is also one of the important application, where you can study the reaction mechanism with the C13 spectra, right? So here like the sigma complex. So in the electrophilic substitution reaction, so in the aromatic electrophilic substitution reaction, generally we get this sigma complex, because the after substitution of the nitro group ipso attack, right? So where this right, so this particular nitro group is attacked at this ortho position, so we call this the ipso attack, right? So this is your ipso attack here. So ipso attack resulting in the formation of sigma complex, right? So it is resulting in the formation of sigma complex here, and that will be differentiated with the C13 spectra. Okay, so where the carbons, right here, the chemical shift of all the carbons, because it is right. So right, so here in this particular, right, so it's what is this? Yeah, hexamethyl benzene, right? So hexamethyl benzene. So it is all are same only. They all the carbons are falls in the same chemical environment. So we get only one, right? So one signal for this hexamethyl benzene here. But the substitution, ipso substitution of the nitro group, resulting in the differentiation of all the carbons here, right? So it attacks it to generally the nitro group brings the changes. Okay, it affects with the ortho and para positions here, and the meta position is not affected here, because this particular nitro group is a meta directing. Okay, the nitro group is a meta directing group, so it won't affects that particular meta position here. So ortho para positions gets affected here, and here we get the del means this carbon, right? So previously, before attack of the nitro group, this methyls are appear set to 205 delta value, but after attacking this nitro group here, okay, so where this carbon is showing the delta value 98.7. This ipso carbon is having the 98.7 delta value, and the ortho carbon 181 and 142, 205. So all these are the different values. We get this right. So four signals for this one. Okay, we get the four signals. So by this, so what is the conclusion in this? Here is the, so whether the substitution is taking place or not, whether because here you see, right? So here is all the methyl substituted, right? Methyl groups are there on the benzene. There are six methyl groups are there, right? So hexamethyl benzene, right? So and all it is sterically crowded generally. Okay, all the methyls are bulky groups here generally. So whether these methyls are accommodating this nitro group or not, and because there is no okay space for the attacking of this nitro. Okay, there is no space because already all the positions are blocked here. All the positions are blocked in this benzene. Six methyls are occupying six carbons in the ring. Okay, so whether this aromatic substitution is taking place or not. Okay, to get the conclusion for about this. Okay, when you record this spectra, C30 spectra, then we got the uh, four signals here. Previously, we got only one signal. So after addition of this nitrating mixture, okay, after addition of this nitrating mixture, we got the four signals for the same compound. Then we conclude that the substitution is takes place, and that substitution is takes place on the same carbon where the methyl is attached here. Okay. So we got the different signals for this ipso attack aromatic substitution here. And here also same thing like aromatic nucleophilic substitution. So here the generally the nucleophilic substitution. Okay, so in the aromatic compound, the nucleophilic substitution is one facilitated, right? Because the aromatic ring, benzene ring, isn't it itself, it acts as a nucleophile, isn't it? Aromatic ring, benzene itself, it is acting as a nucleophile here. So it won't accommodate the nucleophile, incoming nucleophile. Okay. But if in special cases here, in special cases that aromatic nucleophilic substitution is possible. So what is the special case here? When that particular aromatic group is attached with the electronegative nitro groups. Not only nitro, but when it is attached within electronegative groups here. Right. So here you see in this particular example with the trinitro, right here the trinitro methoxybenzene. Okay, so where this this trinitro, these nitro groups are electron withdrawing groups here, and methoxy it is donating group here. Okay, so where this the incoming group is okay ethoxide group. It is ethoxide group here. It is nucleophile, and benzene ring also nucleophile here. This is also nucleophile. This is also nucleophile. Right. But when this aromatic ring is attached with this three nitro groups at different positions here, then these nitro groups makes the benzene group electron deficient, and having the three nitro groups, the benzene becomes more weak, more deficient here. So it acts as an electrophile. Right? It acts as an electrophile. So the nitro group making that benzene electrophile nature. So it invites or it accommodates your incoming nucleophile here. Okay. And it facilitating, okay, this facilitating for the nucleophilic substitution. And that will be known by your C13 spectra, whether it is the nucleophilic substitution is takes place or not. Whether that aromatic ring is facilitating for the attacking of your nucleophile ethoxide ion or not. So that will be known by C13 spectra. So when we record the C13 spectra and it is confirmed the means substitution of the nitro group here, substitution of the nucleophile. And nucleophilic, SN1 nucleophilic substitution. Right. So here the SN1 nucleophilic substitution. So generally, the alkyl halides. Okay, so in the alkyl halides, we have two types of nucleophilic substitution: SN1 nucleophilic substitution and SN2 nucleophilic substitution. So SN1 nucleophilic substitution means unimolecular nucleophilic substitution, and SN2 is a bimolecular. Okay, so what is unimolecular generally here? Where it is multi-step reaction. Okay, SN1 is the multi-step substitution here. So with the stepwise reaction. Okay, it is a stepwise reaction and it involves intermediate. SN1 involves the intermediate formation here. And SN2, it is single step reaction. We call the concerted reaction here. Single step reaction, concerted reaction. So it won't involves any, or it won't forms any, intermediate here. It proceeds by formation of transition state, right? So no intermediate is involved in the SN2 reaction. Only transition state will be forms there. Okay. So here this in the SN1 reaction of this particular alkyl halides, generally this SN1 reaction, it involves a forms of carbocation. A carbocation, carbonium ion or the carbocation, both are same. Okay, carbonium ion or the carbocation. So it gives the carbocation here. And then carbocation, further it is attached with the nucleophile, like OH minus or the NH minus here, NH2 minus. So whatever. That nucleophile is attacking on that carbocation and it gives that racemic product here. Okay, it gives a racemic mixture because where it is this particular carbocation, formed carbocation, it is planar structure here, right? So it is planar structure. So all sides are equal. So the availability for the attacking of nucleophile from all directions here. So the nucleophile can be attacked from many directions, right? So the OH minus. So it can be attacked from here, or it can be attacked from here, or it can attack from here. So all the directions are free to open or free to attack here. So we get the racemic mixture for this one, right? So means if the OH minus or the nucleophile is the nucleophile is attacked from the front side, we get this nucleophile here. If it attacks from back side, we get the nucleophile. So we get this is the racemic mixture. Okay, and here the question is the problem is where this carbocation, whether so the carbocation, it can exist in two shapes here, two geometry. Okay, so it exists in the two shapes like planar structure, planar geometry, and pyramidal geometry here. Okay, so planar geometry and pyramidal geometry, and generally the planar geometry is allowed, and the planar geometry will be takes place in the SN1 reaction actually, and it so it exists in the pyramidal geometry also, right? So with the inversion, right? So by inversion of this empty orbital, empty orbital is takes place and it gives a racemic product here, right? So that conversion also takes place here, and that is confirmed by your C13 spectra. Okay, so by the C13 spectra, so with that particular SN1 reaction, right? So SN1 reaction where this particular planar structure, right? So in the planar structure, the nucleophilic attack takes place in both sides here, from front side and the back side here. Okay? And it gives a racemic mixture. And in the if it is in the planar structure, we get the both attacking of the nucleophile from both sides, and we get the racemic mixture. But if the intermediate is exists in the pyramidal geometry here, so no attack of the nucleophile will attacks from only one direction, either it is front direction or the back direction, whatever, right? So it attacks from the front side only, and it gets inverted, right? The pyramidal inversion is takes place, right? So it undergoes some pyramidal inversion. Right? The pyramidal inversion of this intermediate carbonium ion is takes place, and we get the racemic mixture, right? So that pyramidal inversion is confirmed by your C30 spectra. Okay. So this we can confirm the intermediate geometry also by C30 spectra, and stability of carbonium ions. Here the stability of carbonium ion. So in the carbonium generally we know that where the quaternary carbonium ion is more stable, then tertiary, then secondary, then primary. This is the stability. That stability of this carbonium ion means in plane in general carbonium ion. Okay, in normal methyl containing carbonium ion. So the stability order is this one: quaternary, then tertiary, then secondary, then primary. Here, when they are attached with the different groups here, so the stability order we can see here in this order. We see with this tertiary carbocation with the delta value 327 here, and with this in the secondary tertiary secondary carbocation with hydroxy group attachment here with the 248, and here the phenyl attachment 253, and here is the two phenyl groups 227, and two phenyl group, one hydroxy group with 207 here, right? So with the stability is, it is varied based on the attachment of the group which is attached to the carbocation, right? And dynamic equilibrium. So where you see the particular, okay, so the carbon means carbocation, so it gets inverted, okay, by involving in the resonance here, right? So at a dynamic equilibrium, the position of that the charge, okay, sign of the charge is changes because it involves in the resonance here. Yes. Next, degenerate rearrangement. So here the degenerate rearrangement, nothing but where the changing of, right? So changing of the position of the groups here, changing of the position of the groups here, and the degenerate rearrangement, nothing but where the starting metal and the end product are same. Okay, so here the rearrangement is takes place, but the both are same here. Reactant and product both are same. That is called a degenerate rearrangement reaction, and just and this rearrangement reaction is takes place under thermal condition only in the presence of a base. So it takes place under thermal condition, and how this pathway takes place, right? So here you see, because right, so here this particular some keto esters ether, right? So the keto ether, when it is going to convert into again the keto ether only. But one thing is here, for example, if you okay, if you label this one, this is 2, this is 3, this is 4, 5, 6 here. Here also you label this same thing 1, 2, 3, 4, 5. So what happens here? product, the label one contains that ether linkage here. Okay, ester, not ether. Yes, ester only. So this kind of, right? So this kind of rearrangement is called the degenerate rearrangement. And this rearrangement is takes place by following two pathways here. So you can see the pathway one, right? So here you see where the enolization. Okay, so the pathway one involves the enolization. Okay, so where this yes, right? So here this CH bond shifting here, then this, right? So it becomes OH here, and where it forms. So enol formation is takes place, right? So here the enolization, right? So here it's shifting here, then this is shifting here, then the sequential shifting of the means bonds is takes place. And we got this intermediate compound. Again, that here we got this right. So the ether linkage, then the cleavage of this ether linkages by shifting of this OH towards this, then cleavage of this bond is taking place here, and we got this. So we got the rearranged product. Okay, we got the rearranged product here. This is one pathway, one type of. Okay, and the pathway two explains that, right? Where what is happening in the pathway two. Okay, so how it is takes place here. So yes, so here in the pathway two, first the phenol formation means this. Okay, the enolization is takes place. Okay, so in the pathway one, where the sequential shifting of the bond is taking place, but in the pathway two, first the enol formation is takes place, right? So then after formation of this enol, okay, so then this particular enol rearrangement here, right? So this double bond, yeah. So here is double bond shifting towards here. Then the cleavage of this what is it ester. Okay, so cleavage of ester bond is takes place, right? So in the previous case, in the pathway one, here the ester bond is not cleaving here, right? Ester here also cleavage of ester. Yeah, ester the oxygen, right? Ester oxygen bond cleavage is not taking place here, but here the ester oxygen bond cleavage is taking place, and we are getting same. So this is that particular degenerate rearrangement is explained by this particular uh, C13 spectra, and how you differentiate this happening of this mechanism, where the okay, so in the reactant we have the okay in the C1, if you label this, okay, if you label this carbon C1 here, here this is a C2. In the C13 spectra, generally the C1, okay, the C1 appears in the range of 220 or 206, whatever, right? So 260, whatever, right? Or here is appears in the 216 nanometer, sorry, ppm, 216 ppm here. And in the here C1, right? So here is the ether C, okay. So this particular OCO, here is the ester. Here is a ketone, right? So here is the ester. So ester oxygen is there, ester oxygen. So where the 216 is absent here, right? So by this you can know that some rearrangement reaction is taking place. Some reaction is taking place in this particular reaction compound here, right? So that will be known by this C13 spectrum. Okay, and carbon ions. So here the carbon ions are like negatively charged species. So you can identify with this C13 spectra. Okay. So this is your C13 spectra, and the 2D. So the 2D NMR spectra we'll see in the next class. Right? So 2D multiple techniques in the NMR spectra, that is also one of the important and some difficult than this C13 spectra. Right? The multiple techniques in the C13 spectra, that is okay. So it's somewhat difficult spectra topic, that one, and ORD spectra. Okay. So and in the ORD spectra also we have the octane rule. Okay, two alkyl ketone effect. So some important questions is there in the ORD spectra, and in the multiple techniques in the NMR spectra, like 2D NMR spectra, we have the rosy spectra, nosy spectra. Okay, 2D inadequate spectra. Okay, APT spectra. So different, and what is that? Nosy. In that heteronuclear and homonuclear, cozy spectra, also correlation spectra, resolved spectra, correlation spectra, 2D inadequate spectra. So all things. So very somewhat interesting topic, 2D NMR spectra. It is interesting and it is difficult here. Okay, so we'll see in the next session. So I'm stopping here.